So hi everyone. Yeah, my name is Dipankar, and I'm very excited to be here and talk about interesting project, which is for like data lake and data lake house architectures. It's called Apache Iceberg, and what the idea would be today to like go through like what's the table format and understand like all this time we have had like a table format from Facebook, which is like Hive, which was pretty like the de facto standard. But now why do we need a new one, right? And like those kind of stuff. We'll go through the architecture of an iceberg table and understand like what these components are that kind of makes up iceberg, right? And what happens under the covers when I do like a create operation or any kind of like a DML operation, right? So that would be the goal. Finally, we'll end up with the result benefits of this design and see how like Dremio fits in here and like maybe help understand and solve this problem. So, a little bit about myself. I'm currently a developer advocate at Dremio. I'm involved in open source projects like Iceberg and Arrow, and I'm pretty much involved with the community and open source part. In the past, I have worked in various roles like BI and data science and data architecture specifically. And I am very much like available on LinkedIn or Twitter in case you have any questions. That I may not be able to answer today in this particular session. So I just put up a QR code just in case you want to reach out to me over LinkedIn or Twitter. With that, we will start with understanding what's a table format, right? So usually with databases, we have seen the concept of tables, right? It's not a new concept at all. Like companies such as Oracle, Microsoft, they have been doing it with the relational database for a while, right? And basically, it's a way to organize a data sets file to present them as like a single table, right? So users don't really have to know about the physical bytes and files, and they can just have that abstraction on top of that, right? And like I said, in the past, database vendors like Oracle or Teradata had their own storage engine handling the data files on the disk, and then they had their own execution engine, right, which interacted with those files. Now, in the big data world with Hadoop and HDFS, we ended up ultimately with the Hive table format, which you know a lot of people can now have access to the data, right? Because like you need some level of abstraction on top of that. So engines or users can interact with the data, and Hive provided a way and abstraction to do that. So basically, that led to the rise of the table format for Hive, right? And it allowed democratization of like data using Hive QL, which is similar to like SQL, and it gives the ability to analysts to run a report or whatever it is. So with Hive, we have a table. The structure that how it looks like in a Hive table format, it's basically a directory. Okay, so all the files that lands up in a data lake, they are basically managed in the form of a directory. Okay, like you can see from the screen later the shot here, right? That it's a table, and you have a directory, and within the directory you have a set of files, right? So let's talk about this in a bit of more details, right? So in the Hive table format, the table content, like I said, is like the files are in one or more directories, right? Here we can obviously see one of them, but in at scale this would be a lot of directories. And the tracking of this particular direct files are done at the folder level, right? Whatever is there in the folders, right? They are tracked in that way by the engine. And this has been the de facto standard since the mass adoption of Hadoop, like I mentioned. Like Facebook bought Hive for SQL and Hadoop. You did not need to have like the MapReduce jobs that you were basically writing off to like process the data, and it allowed to like data to be used by a lot of users like analysts, right? So definitely, it being the de facto standard has some reasons behind it, right, and advantages. And we're probably gonna like look through a couple of pros and cons. So first, it works with basically every engine, right? And there was no other table format until this point of time, right, to allow that. So it basically worked with a lot of engine. Like you can have Hive, even the Hive engine to work with that, or any other engine. It also have more efficient access patterns, right? Things like partitioning schemes and mapping that to a column or bucketing, or you don't have to do full table scan for every query that you run. So those kind of efficient access patterns were there. It's also file format agnostic. You can use any file you want, whether it's Parquet or CSV or JSON, doesn't matter. And the most important part was that it allowed atomically to be updated like a whole partition, right? So for example, you can take a whole partition, change the data, whether you want to insert some record or delete something, and write that into a new partition. And when you're writing it, no one sees the changes, right? And then you can atomically swap that reference in the metastore. And this is how basically the Hive metastore came. And in case you're not aware of Hive metastore, and that allowed us to get the atomicity and consistency and all type of guarantees like with every query that we run and those kind of stuff. So Hive Metastore provided a single central answer to what's in the table, right? Hey, you know what, I need to understand what's the content of the files and what's happening. Hive Metastore was the kind of the single answer. But Hive also brought in certain disadvantages, like smaller updates were kind of inefficient, right? Because you can only atomically update a whole partition. If you only want to change a few rows and a lot of times, then it's very inefficient, right? Also, you had no way to change the data in multiple partitions safely. So basically, no atomicity guarantees if you want to insert a row in two different partitions. You cannot possibly do that without those atomicity guarantees in Hive. And the same thing goes with like multiple jobs, multiple engines trying to modify the same data set. They're not safe for those guarantees and trust in the data. And in the Hive table format, like the files are under folder, like I mentioned, but engines can only read file, right? The files, they cannot read the folder. They have to go to that file level. So engines take a really long time to read by and go under each of the directory and try to understand what's happening. And we will deep dive more on use case by Netflix later, like which is basically what led to Apache Iceberg and what we have now. Um, so these are kind of the cons, and use again, one of the most important con that I kind of personally saw is that you just need to know the physical layout of the table, right? So for example, with partition, right? If you have a table partition by day and your table has data in like timestamp format, it will do a full table scan unless you just explicitly mention that partition column in the query cause, right? Because the engine doesn't really know if there is a mapping with that particular timestamp to that, physical transitioning partitioning scheme, right? So you end up with very expensive scan. And at scale, this would be like a huge problem. On more importantly, you need to educate people as well, right? You need to tell analysts, okay, hey, you know what, this is the physical directory, and this is where the partition is, and this is how you can query it. So this is really cumbersome. Also, the table statistics that Hive collects are often stale, or those are basically like kind of a asynchronous periodic job. So by the time you run the job, the statistics are invalid. You cannot really take advantage of query planning and everything. So how can we solve this problem? These problems are pretty much common in every organization at scale. I personally have seen it in the various organizations that I've worked with, and Netflix were kind of the main one to look at this problem. So they went to the drawing board and they were like, thinking that instead of putting band-aids on each of this problem, can they take a step back, right, and try to understand what's the actual issue, right? Because in the long term, it's going to be really difficult. Like when the data is increasing, you have a lot of data coming in, a lot of engines working at the same time. It's going to be really hard. So they had some goals that they wanted to achieve, right? And these goals were basically like they needed table consistency, correctness, right, or consistency, right? They needed to have the trust in data. Like for any organization, I think it's super important to have that trust in the data so that they can make that data-driven decision makings and stuff. So any query that I run or anyone else run should get me the same result, right? Next was faster query planning and execution, and like one of the use cases that I'm going to like talk about a bit later is that one particular query took them 10 minutes just to plan, just to plan that query for a week of data and for just one single metric. So users are not going to wait for that long, as performance is really the key, right, in this type of stuff. And most importantly, they don't want to worry about the physical layer of the data, like I was mentioning with the partitions, right, with Hive. If I have to query using a date, users should not have to worry about that. Can we just have the software, or some automation take care of that? Because users don't need to know about the partition just to query simple one day of data. And there were also a lot of problem with table evolution, and this is something we usually see, like tables grow over time, right? They have different requirements, schema changes, or whatever happens. We need to embrace that, and we should be ready for that. And most importantly, they wanted to accomplish all of these at scale, right? We can take care of a very small data set or a very small data lake data that we have. But what if I had a huge petabytes of table of data, and it only grows, right, with time? And considering Netflix, it's a huge organization as well, like, so it's going to be huge. So when looking back on all this, intermediate solution and band-aids and everything, and what they went through, is that the problem that they were kind of like trying to understand is that all these cons, they could really solve it by basically a simple hack. The problem with the Hive table was that it was tracking everything at a folder level, right? So instead, if we could track everything at a file level, this problem would be solved. Like these problems, like a lot of this problem would be solved, and that's the core of Iceberg. Okay, so you can really mitigate this cons with this small change, and Iceberg comes into play with this kind of like solving problem. So coming to what Iceberg is and isn't, it's better to have that context, right? It's important to have the context right, because we have seen that Hive is quite nebulous as a term, right? It can mean different things to different people. It might be the Hive engine or the Hive table format or whatever it is. So what Iceberg is and isn't, it's a table format specification. It's very important to understand that it's a way to lay out the bytes in the form of table, right? That abstraction that I was talking about. It's a set of libraries and APIs for interaction with that specification. So, for example, your execution engine or your processing engine will leverage Iceberg APIs and libraries to interact with it, right? And do things like compute or like process or whatever it is. It's not a storage engine. It's like not an execution engine or service like Spark or whatever it is. Like it's not a service as such. So as you can see in this image here, right, this is a high level architecture of Iceberg, and we'll go through like the top to bottom and try to understand the various components of Iceberg, and at the same time we'll also focus on what happens, really when I query your data and read the data, right? So we have three basic layers here. One is the catalog layer, the first one. Then there is a metadata layer, and then there is a data layer. Okay. So the first thing here is the Iceberg catalog, and it's super important. So if a user is trying to either read or write data from a table, they first need to know where they have to go, right? That's the first thing. And catalog is that place. It's a store that kind of houses the current state of the table. Hey, the the concept is that you can store as much of data in you as you want in a data lake like S3, which is like super cost effective and scalable and everything. But you need some locking mechanism, right, for atomicity and those ACID guarantees that we were talking about, right? And so that consistency is super important, and Iceberg catalog serves this purpose. So the catalog can be a lot of things, right? But there is a key requirement. It must support atomic operations, to update that pointer of the current metadata. And there are different kind of catalogs, like HDFS can also be a catalog. Hive Metastore is one of the common one that we see, Nessie or Glue, or for that matter, any kind of like relational database as well, as long as it has a locking mechanism. Uh, we also introduced something called REST API catalog, which allows you to basically have that API. You don't need to like implement every single time a catalog for every single product that you bring in. So in terms of what it contains, like I mentioned, it is the mapping of the name to the location of the current metadata file. So for example, it basically will have, the reference to the current state of the table, the metadata file that I'm going to talk about. Okay. So for example, let's say you do like a select star from this particular table with some limit, like with 25 like limit. So what you do is you go to the catalog and basically ask the catalog, hey, can you give me the current location of the metadata file? Like, can you give me that location? Because that's the current state of the table. Okay. So we go on our way, and once we start with the catalog, we now have the location of the current metadata file. Let's say the metadata file is this particular metadata file, right? The number 3 that you see over here. So what is a metadata file? A metadata file, as the names kind of like specifies, it stores metadata about a table at a certain point of time. And it is super important. Like, the whole point of having a table format on top of the data lake is to have that metadata benefit, right? And you can see some of the contents of the metadata file over here. Like, this is obviously not a full, file, but just an excerpt. But you can see some of the important things like snapshot, like the current snapshot ID, right? And just to give a brief intro about snapshot is basically the state of a table at a given point of time, at a certain point of time. So basically whatever operation you want to do, like for example, if you are creating a table with a create statement, right, or adding a record, inserting a record, or deleting, everything is captured as a snapshot in Iceberg. Okay, so you see like information like snapshot ID, the current snapshot ID, which basically tells you like, okay, this is my current state of the table, right? And from that you get the snapshot ID and the manifest list, as you can see here. And that's the next information that I need from this particular tree in the hierarchy that I need to go and find to the actual data files. So the next thing that comes up is the manifest list, like from that particular metadata file. So manifest list is basically a list of all the manifest file, and within this particular manifest list, we see things such as like the manifest file path, as you can see on the right hand side, when it was added, and partition specs, which is like super helpful for something like partition pruning. You don't really need to like go to the actual data file unless until you can like basically prune it at that level, right? So now we have the manifest list, like from the metadata file, we went to the manifest list, and then we have the manifest list, and from that we are getting the manifest file path. Okay. So now from this particular manifest path, based on the particular snapshot, we'll, let's say this is our manifest file. Okay. And this manifest file, basically, if you see the content over here, it gives us the list of the actual data file, all this Parquet file or this org file or Evro file, whatever it is, that was landing in a data lake, now is being referenced using those manifest file. So for instance, we see things such as the file path. That's super important. We need to know the actual file path, the format of the file, whether it's Parquet, Evro, whatever it is. And most importantly, some of the statistics, like, the null value counts, whether it's a lower bound of the table, like the column, or the upper bound of the column. And these are super helpful, like I said, in terms of the pruning of the file and avoiding scanning of all the file. This makes queries super faster, and, your optimizer will be pretty much dependent on this manifest file to like have those level of like, faster operations. So if I have to talk at a leaf level, the manifest file, it keeps a track of all the data file, the actual data files, right? And now for our select query, which we were talking about initially, like the flow that we kind of saw is that we went to the catalog, We asked the catalog, hey, give me the current metadata pointer, like give me the current metadata file. From there, I got the metadata file, and then I got the manifest list, and from there, I went to the manifest file, and finally the data file. So that's the entire like the flow. And this may seem like a lot, but this is a way faster at runtime, and it's super fast. So now let's understand like what happens under the cover with some example, and that would like set a realistic expectation on what happens underneath, right? So for example, let's go and start creating a table. Like that's the first thing we probably would do, that creating an iceberg table, right? So we will run this particular create statement. Like it has a couple of fields, and you will see on the right hand side the diagrammatic flow. Like I'll basically like talk about what happens and the diagrammatic flow of it. Okay. And on the left hand side, as you can see, that's the catalog, where that's basically the current metadata reference, as well as the actual file system. For example, this is, let's say, your data lake, right? You have your file and metadata and everything. Okay. So we have this particular create table statement, and we run it, and we have partitioned it by a particular partition as well. And it's a reference on that particular order timestamp. As you can see, unlike Hive, where you'd have to like specify a different column, here in the partition we are using the same column and the same, and we are just using a transformation on that. Okay. So basically, when I run this particular query, it creates the table and it adds some metadata file, as you can see here. Okay. And the whole reason, that the metadata file, obviously, it has its all like schema and details like we saw in the previous slide. But we haven't created a data file yet, right? We haven't inserted anything into the table. So that's why we just see this particular structure and not the entire flow, right? And as you can see, in the table, in the file, file system, you will probably have two folders, which is, one is the metadata folder with the metadata file, which is a current file. And there will be a data folder which is empty right now because obviously we haven't inserted anything. Now, if I go and insert something, right? If I run this particular query, what happened is, basically, if I run this query, I'll see this particular tree structure, right? So what happened is, whatever engine we use for executing this, right? Like I said, like you need an engine to execute this particular, insert statement. So it can be Dremio, it can be Spark, anything else as well, whatever it is. What happens is, it basically went and wrote the first data file. The engine, basically, when it runs the particular command, it goes and writes the data file, as you can see in the data file as well, in the file system, right? And also the engine knows about the statistics, right? We were talking about the upper bounds and the lower bounds and the null value counts and those kind of stuff. So the engine has those information. It creates the manifest file with all those information that it kind of just wrote, right? So as you can see in the file system as well, in the metadata file, the engine basically, wrote that manifest file with all those information. And with that, it created the manifest list, which is basically keeping a track of all the manifest file, as you can see here. These are all Avro files. And then when it comes to the metadata file, remember, in the beginning, we only had this particular metadata file, right? With the previous create statement, right? So now with the new insert statement, we have a different metadata file. So what basically it does, Iceberg internally, it takes the previous snapshot, right? And it basically replaces that and amends that new one with the new information and creates a new metadata file, which is the new metadata file that we see over here. So now we have two snapshots. One is when the create table was executed, and another one which is basically the insert statement that we just did. And all this is created in a new metadata file. Finally, the catalog, as you can see, is updated with the version 2. Initially when I run that create, it had only the version 1 of metadata, right? And now with the insert, the reference has been changed to current, this particular metadata file. So initially it was pointing to this. Now Iceberg pointed to that. So that is the current state of the table. Okay. So that's like the overall idea of an insert. I can also like run through an absurd case, which is pretty much again a very important query, which is merge into. You have situations when you want to like do some absurd. So it's basically like, let's say you ingested some data into a staging table, right? And you want to do a merge into, like, so what happens is, like, hypothetically, let's say we have a order ID table, right? Order ID field. And if there is a match between the staging table and the production table, what we do is we update that particular order amount. And if there is no match, we are going to just insert. So that's the absurd operation. Like, it's update and insert. So when I go ahead and run this particular statement, like, I already have the new kind of like structure. Before that we had this. When I run this particular query, I can see that there is a new tree hierarchy form, right? So we kind of see the same flow again with the same iceberg tree, from the data files to the metadata files, like the entire flow over here. And we can see we have two different partition here. And I just wanted to like explicitly mention about that, because we had partition by date, and this is more of a hypothetical scenario. Like, we still see the original data file, which is what we have in the gray one here, right? It is still there, right? We actually have took that, and we kind of like, when we did that update statement, the merge into with that update with that order ID, if we took that older one and we rewrote that, we had a new one now, Okay, but that is now, even the older one is still there, it is still there for us to use it, right? So finally, the second hypothetical statement was like, okay, if we didn't have any order ID that matches the production table, what we are going to do is we are going to insert it into as a new record. So considering that it's a new partition, by a different R, so we inserted it into a different, partition. So it's just an idea to like, show like how partitioning works and how you have to like, how you can prune things and accordingly. Okay. So this is basically again an idea of absurd. Now, one of the most common scenarios, obviously, you want to read the data. You obviously like had an idea of like how write works, and we have seen like insert and merge in into. So now let's try to understand how a select query works under the hood with Iceberg. So for example, a user says, hey, you know what? Give me the orders from January 26, 2021, right? So going back to the Hive world, if we had such a statement, Hive would say, well, I'm not partitioned by date. I'm partitioned by R. And the partition would probably be something like 2021 slash 01 slash 26 slash 08 or whatever hour, right? And you'd end up basically reading the entire table unless you specify that in the statement. Hey, you know what? I need that particular hour. I'm providing that column query here, right? Which obviously is a huge problem at scale, right? But what happens with Iceberg is that we'll go through the same kind of flow again. Like we try to understand like what happens. So with Iceberg, we go to the Iceberg catalog, right? And we go to the catalog and get the current metadata pointer, which is what we want, the current state of the table, right? And from that, we retrieve the same metadata file. And from that, we get the manifest list. And when I get to the manifest list, I get the manifest file as well. And in the manifest file, I will have like information like partition spec. So Iceberg actually keeps a reference to this partition, right? It understands that this is partitioned by the field order timestamp, but the field is an hour transform on the order timestamp, right? So engine can use that information and know that basically that if they're asking for that particular date, it can effectively look for that partition and go for that hour, whether it's like from 00 to like 23 hours based on the particular timestamp, right? And that way it avoids scanning all the file. For example, in this case, I just need this particular data file, right? I don't need this guy, so since it's in a different partition, probably I don't even need to go to that particular folder and make our queries very slow. So the key really is storing that reference of the transform in this kind of like scenario, and Iceberg does that pretty well. Now, another important use case is basically, it's a snapshot thing. Like, how do we go back and, do things like time travel, right? Time travel is a really important aspect with data warehouses. And, in general, we want to go back in time and like understand, for example, if you have a financial, end of the quarter or something, you want to do a reporting on top of that, like a Tableau report or something. You want to go back and see, hey, you know what? I want to like get the data that was there for a particular, quarter. And Iceberg allows you to go back and you do those time travel because it has been historically maintaining that information, right? So if I run this particular statement, which is like select this from this table as of this particular timestamp, right? I want to go back and do this. So what Iceberg will do is it will go, let's say hypothetically, let's say this is particular timestamp that is before like the merge into that we did and after the insert, right? So that's the hypothetical scenario. So now Iceberg is going to follow the same path again. Like it goes to the catalog, it asks for the current metadata pointer, and from that it opens the metadata file. And now in the metadata file, let's say it gets to know, okay, this is this particular timestamp. From that metadata pointer, it opens up that particular metadata file. Okay, and since Iceberg keeps a list of all the snapshot in the snapshot array, remember the array that I was talking about where we look for the current snapshot ID? It will basically check for that particular user request and say, okay, it's for this particular timestamp, 26, May 2021. So I'm going to say, okay, this is that particular snapshot, not this one. Okay. And once we have that, we'll use that snapshot to get the manifest list info and the manifest file, and finally the data file. So this flow is quite similar to what we saw with the select star query, with the read query, but this time the user has a slightly different request, right? It has a request to go back to a particular timestamp, right? When the data was there, right? And like Iceberg does it pretty well. Like it maintains all those snapshots. Now again, the question might be that, okay, we might end up with a lot of snapshot over the process, right? We might have a lot of operations going on, like even for things like streaming data, right? There are going to be a lot of small files problem and those kind of stuff. So is there a way to maintain this snapshot and expire some of them, if not, if something that is outside our scope from our company's requirement? For sure, yeah. I mean, you have like Iceberg provide APIs to do that by default. So you can use things like expire snapshot, which allows you to expire snapshot and go back and maintain those files. So we went through the different CRUD operations and the path Iceberg follows to, let's say, have an understanding of how to read a file, to write a file, and those kind of stuff, right? Now let's see how things look at scale and in production, right? I was talking about this use case from Netflix, and this is actually straight from a slide from Ryan Blue, who basically created Apache Iceberg back in Netflix when he started there. And so if you look at it, basically, it's a case study. It's called from a system called Atlas. It's basically the time series metric system from Netflix's operational system. Okay. So it's just 1 month of data, and it has, like, you can see it's like close to 3 million files in probably 3,000 partitions, right? And their problem is that they cannot process more than a few days of data. That's the problem, right? They have a huge amount of data in just a month, and they cannot process it. So if you look at the simple query, it's a pretty straightforward query, right? They want to, like, get a few tags, based on a certain type, and they have a certain metric, just one metric, and they have a filter. It's basically just a week of data, as you can see, from 22nd of August to, like, 28th of August. So it's February. So it's pretty much like just a week of data, which is should have been pretty straightforward as well, and shouldn't have taken much time, right? With Hive table format, when Netflix had the Hive table format, this particular query, it took 10 minutes just to explain the query, just to plan the query, and not even execute it, right? So just getting the files and planning the query takes the majority amount of time. That was the main problem, right? And no one is gonna wait like 10 minutes to like even plan the query, not even get the results. It's kind of like unrealistic, right? In that way. When Netflix implemented Iceberg, this particular same query, it took them like 13 minutes to execute the query, not plan, just execution of the query, right? And the planning time was just 10 seconds. So really, from 10 minutes of planning time to 10 seconds, that's like a dramatic improvement, right? And that's a huge improvement that they saw. And that's with just partition data filtering, not even things like min max filtering or the manifest file column statistics that I was talking about. So if they basically then implemented partition and min max filtering, and what they saw is that the entire execution time, like to process the query, it took them 42 seconds, just from 13 minutes. And I believe that's a huge improvement. When we're only planning just took 10 minutes of the time, and now the entire execution with planning like takes 42 seconds of time, which is pretty impressive at scale as well. And you can imagine, when the data grows, and how they might have. So this is the use case that I was kind of like, that kind of like the inception of Iceberg, and how it came into picture, how it solves those kind of high problem that we saw before. And that's, I think, really a segue to like implementing Iceberg. So another kind of key capability that Iceberg provide is the ability to do compaction, right? Compaction is a known problem that we have seen in the big data world. I personally have encountered it a lot of times with small files where we had a Hadoop file system, and we had a lot of small files coming in because of the whatever limitation we had. And that's an overhead, right? Every time your query needs to open a file and it read this small file, which is pretty cost intensive at scale, and there are a lot of like side overheads as well. So the concern here is, your writers and even readers, right? They need the fresh data, right? So get a row, write a row, right? That's the ideal scenario. But the problem is the fixed overhead on both the read and the write side is super high, right? So when working with data, like there's always this read side versus the write side trade-off, right? You want low latency in the write side. So you basically, let's say you get a record, you want to write it, right? And if you do this for every record, you will basically end up with one record per file, which leads to a lot of small file. And that's kind of like the extreme of the small file problem. And on the read side, you want high throughput, right? You don't care whether it's, too many records in one single file. You don't have to pay the downside cost, right? So that's what you want. And what compaction in Iceberg allows you to do is to balance this write and read side trade-off, right? So Iceberg says there is no problem with writing more data and creating small file. But what Iceberg APIs will enable, like I was telling, is to compact those small files, 100 small file into one large file or whatever it is, right? So in the read side, there is this high throughput and it's super fast. And this is all asynchronous in the background, right? Users are not even impacted. Like they don't even need to know about it. Versus in Hive table format, where we saw like, compaction or like, update at one single time, and update to like one partition, and, one particular job can only happen at one single time. And with Iceberg, you don't have to worry about that, any of that. All these are asynchronous. So users always see the fresh data. And also the read throughput is super high, right? So really good performance. And a key thing to note here is that Iceberg is not an engine, like I was telling, right? It's basically a set of APIs. So any kind of scheduling or triggering and compaction work has to be done by external tools. Like, like for processing, you might use Spark or Dremio, or like, any kind of scheduler for that matter. Now, we saw some of the production use cases. We understood the architecture a bit. Like let's see and understand like some of the design benefits. What exactly makes Iceberg kind of like stand out, right? So first of all, you can efficiently make smaller updates, like you can make changes at a file level and not the partition. And files can only get so big, right? 128 gig MBs or 256 MB. So you can make a lot of changes effectively, right? So that's the best part with that. Next, snapshot isolation. So the reads and the writes don't interfere, right? In Iceberg, as you are writing, the reads aren't affected, and vice versa. The writes are also atomic, right? Hence, you don't see things like partial writes, right? You don't see like zombie data, right? It also gives you like things like concurrent writes. Multiple people can write at the same table at the same time. Multiple engines can write at the same table at the same data set, right? It uses things like optimistic concurrency control and checks and stuff like that. It also enables faster planning and execution. The key here is that the list of the file is defined on the right side, right? And OLAP analytics is like write once and read more number of times. So Iceberg questions about that cost. Like, why do we have to collect all the stats when reading, when specifically we know we are going to read like 1,000 more times than we are going to write, right? So it gives that read side benefit, right? And same thing for statistics, right? Instead of an expensive like a read job, why not do it during the writes? And that's what Iceberg does, right? It already knows details about the data, right? About the minimum and the maximum number of like the values, the number of NaN values and stuff like that. So let's do it on the right side. That's the whole concept. And because of that, we also get reliable metrics, right? Instead of expensive reads, do it on the right side, right? This is a huge benefit for all the query, cost-based optimizer. Any query that you issue at scale now has the right join order as well. That those kind of like are important things. Another important thing is that with Iceberg, we abstract kind of the physical view and expose a logical view to user. And I think that's super important. User don't need to know about things like hidden partitioning, for example, right? Where with Hive, we saw like users need to know about like the physical layout. And as a user, as an analyst, you don't need to know that. You need to have that abstraction, right? So this also means like the things like table evolution, right? We didn't touch upon that much here, but Iceberg supports full table evolution, right? So you can change the schema or whatever it is, like you can evolve as you want. You can even like do things like partition evolution, right? And with Hive, they're all, I believe, are file dependent, right? For example, if you want to make changes to a table with a CSV file versus a Parquet, it's all going to be handled slightly differently. And I think that also leads to a lot of other problems. So it allows for schema evolution, partition evolution, and even like coexistence of two different partitioning schemes. So really like total flexibility, and data engineers can now transparently experiment with the table layout, right? They have a way to like do more like focus work in terms of the platform and architecture and stuff. And like I said, like the rich schema evolution is a part of it. Like we talked about it a bit. Also, the most important thing is that all engines, they see these changes immediately, right? It's a very lightweight operation. Like, no matter, for example, if Flink, you are using Flink to like write some streaming data, and you are using Dremio to like query some of the data, you don't have to worry about whether I'm seeing the right data or wrong data. All the engines, they see the changes immediately. That's the best part of it. So that is pretty much all, like in terms of the design benefits, what Iceberg does. Coming back to the point, what Dremio does, and what my company is basically working towards, is that the problem with this lakehouse architecture that we see, with like the whole idea is that now with data warehouses, we were like putting all the data into a warehouse where it's limited to a particular vendor's proprietary engine, and you're locking yourself with the data files into that particular storage engine, and it's super costly, right? Even to execute a simple query, it takes a lot of compute money and stuff. However, with data lake, we saw that problem gone, and we have the option to like take up something like S3 or ADLS or any kind of compute, like cloud compute environment, and scale it up as fast as we want with like lesser maintenance effort and all this stuff. But with the lakehouse architecture, that kind of like adds a level on top of that. With the data lake, it can lead to like issues like data swamps and stuff. So with the lakehouse, it kind of makes everything easy. So the whole problem that Dremio is trying to solve, and like the entire industry is kind of like bending towards, is that how do we solve this friction of getting started with the lakehouse platform? How do I, okay, so for example, I adopt Iceberg, how do I get started with it, and like make things simple for analysts and everyone else who can do analytics on top of that, right? So with Dremio lakehouse platform, it's super easy, right? What you can do is you can like dump all your like files, Parquet file that you have in your S3 lake or whatever it is, ADLS or any kind of like open source or whatever it is, and you can just connect Dremio Cloud directly with that storage, right? From the UI, it's an intuitive UI as well. And you can connect to the particular source, and you can start creating Iceberg table. Like you can, as you can see, you can create a simple table like this, and it's as simple as that. Like using things like SQL, like which everyone in data loves, right? So Dremio allows you to even like natively connect to like BI tool like Tableau or Power BI, or whether it's preset or superset, whatever it is. So you can start building your dashboard directly on the Lakehouse platform. You don't need to worry about, okay, in the initial world, how things is to deal, or how personally I kind of like used to deal with things. If I am like a BI engineer, I would request for a data to be moved from a particular data lake to a lake, particular warehouse, and it would be like a couple of weeks. And from that warehouse, it might need to be moved to a mart, or like into some kind of like a faster processing environment. And then from that, I can like use a tool like BI tool like a Tableau or Click or whatever it is, and build on top of that. But with Dremio, it's a native integration with all those BI tools, so you can directly connect to the lakehouse data, and you can start building on top of that. And that is pretty much it that I had. One of the important things that I wanted to share just before I end is the additional resources. Okay, so how do I get started with Iceberg? That's a pretty common question that I get, is that there is obviously the Iceberg official page, iceberg.apache.org. And we recently had the 1.0 release yesterday, and it was a super important release as well for everyone to like really adopt. And obviously, like, people have been using, like, in terms of production use cases, we have customers like Apple who are hardcore into like Iceberg in production, Stripe, Netflix, so it's there are a lot of companies that are adopting Iceberg in a production environment as well. So Iceberg official page has a lot of important information. We've contributed a lot to the community pages as well, like, whether it's in the form of blog or code or whatever it is. In Dremio, we have a page called Subsurface, which is basically a site where we do all things open source, like whether it's Arrow, Iceberg. I personally write a lot in there as well and share some of the interesting insights. So that's pretty much it. And if you want to like get hands-on, there are like a couple of examples as well. And always reach out to me, like, in case you want to adopt Iceberg, and you have some questions around that. I'm happy to answer as well.